The title of my talk is Current Remote Attestation on IoT and TrustZone Opti with VERAISON Verifier. This work is collaborate with Ao Sakurai and Yuichi Sugiyama. This slide shows today's contents. At first, I want to introduce remote attestation. Remote attestation is presented in previous talks, but I want to say why do we need remote attestation on IoT? The remote attestation use TEE. TEE is a trusted execution environment. Our development use Opti. Opti is an open source TEE operating system. So we developed remote attestation on Opti with VERAISON Verifier. The implementation requires prerequisite provisioning phase and remote attestation phase. I explain these phases. So current version is general, but I also developed security enhancement version. This version uses HSM, hardware security module. It is good for supply chain security. And I want to conclude this talk. At first, I want to talk about the internet. So this is very famous figure at the beginning of internet. At that time, on the internet, nobody knows your dog. So this figure indicates authentication is very important. Fortunately, at that time, software and hardware assumed to be safe because there is no commercial site and no attackers on internet. However, we cannot, it is not true in the present day. So we need to confirm the soundness of software and hardware on remote devices. To solve this problem, remote attestation is developed. So, remote attestation is a mechanism that confirms soundness of hardware and software. It is also known as software authentication or hardware authentication. Remote attestation is become very popular now. So many devices use remote attestation. For example, your smartphone uses remote attestation, and TPM on PC is use remote attestation. FIDO, smartphone protocol MATA also assume remote attestation. Today's topic, TE, Trusted Execution Environment, use remote attestation because TE isolate the execution environment from a normal operating system. It hides its behavior, so we have to confirm the software on the TE. So this figure explains the remote attestation defined by IETF as a network protocol. So it is defined as RATs, remote attestation procedures. This architecture assumes three players, attester, lying party, and verifier. Lying party want to get a data or service from attester want to get data or service from lying party. So the attester offers its evidence that show the device is sound and the application is good. The evidence is signed by the attester's private key, private sign key. The evidence is sent to lying party. Lying party want to decide the device is good or not, but lying party does not have the knowledge of attester's software and hardware. So attester asks verifier to judge. Verifier has the knowledge of attester's soundness. For example, attester's public key and hash value of trusted application binary. So verifier can judge the evidence and send back to the attestation result to Lang party. After that, Lang party and attester can communicate. This slide shows the TE, Trusted Execution Environment. Trusted Execution Environment is a CPU function. This function isolates the mode of CPU, secure world and normal world. We can run normal operating system on a normal world. On the other hand, secure world is isolated from normal operating system, and we can run a critical application, trusted application on it. Usually, the trusted application is a part of normal application, client application. So, client application asks the critical processing on a TE. So, the TE is a function of CPU, and some CPU for IoT equipped remote TE. For example, Arm Cortex-A TrustZone is a TE for smartphone and IoT. In this case, operating system is assumed to be Linux. Arm Cortex-M TrustZone is fit for smart embedded system. The operating system is assumed embedded OS. Today's target is Arm Cortex-A TrustZone. So, why do IoT devices need TE and remote attestation? Because IoT devices are managed by M2M, machine to machine, without human monitoring. So it is very dangerous. Security should work autonomously and based on hardware security. This situation is same to game. As you know, many game machine equipped TE and remote attestation to confirm the game status because the user are attacker. So we need to confirm the soundness of software and hardware on remote devices. So we need to use TE and remote attestation. Remote attestation allows running confidential software on IoT device. Remote attestation allows confirming the soundness of intended software and genuine hardware. Using this technology, we developed remote attestation on OPTI for Cortex-M, Arm Cortex-A TrustZone. This figure shows the OPTI. OPTI is an open source operating system for Cortex-M TrustZone. It follows the Global Platforms API. It is different from normal world. Normal world OS follows the POSIX API. OPTI had a simple attestation mechanism, but it is not fit to current remote attestation mechanism. So we developed the proper remote attestation mechanism for OPTI. We also use VERAISON Verifier. VERAISON is also open source software based on IETF protocol. So LATS protocol assumes roles and artifact. Roles means player, and artifact is information. And let's assume two phases, provisioning phase and remote attestation phase. At provisioning phase, roles sends the artifact information to verifier. So these information are used by deciding the attestation evidence. At the remote attestation phase, attester sends the attestation evidence to verifier. Verifier decides the attestation evidence using this information and sends the result to link party. And the RAT protocol based on CBOR format, and we developed the CBOR format software on attester TrustZone Opti. This figure, this slide shows what we developed. So we developed a remote attestation mechanism on Opti. We developed the API to create attestation evidence for a TA, trusted application. In order to develop, we use pseudo TA. Pseudo TA is a no, oh yeah, here is a no. Oh, yeah. Sorry, it does not work well. So pseudo TA works as a part of Opti, as a part of operating system. So pseudo TA measures the binary hash of TA, trusted application. And pseudo TA creates attestation evidence with CBOR format. Pseudo TA also signs the CBOR format with signing key. The attestation evidence is sent back to verifier, VERAISON. We also offered some samples to use this remote attestation mechanism: a sample TA, sample CA, sample link party, and sample setting of VERAISON. This figure shows prerequisite and provisioning. So at first, I show prerequisite. So endorsement is built by Opti developer, OS developer. And reference value is developed by TA builder. Opti builder offers signing private key, signing public key, signing key ID, and signer ID. TA builder offers TA ID and builder TA binary. After that, TA builder measures the hash value of the binary, SHA-256. After that, these information set to attester and verifier. In this case, there are two attesters part, TA of Opti and TA. TA of Opti is a signer, and TA is signing a target. So signing private key and signing key ID and signer ID are set to PTA of Opti. TA ID is set to TA, but the hash value is not set because the hash value is measured by PTA of Opti at the runtime. So verifier get all information except signing private key, because signing private key is on the PTA only. So the key management is very important. So this key management is renewed by security enhanced version. I will explain the later slide. This figure shows another view. At build time, TA developer uses a TA ID and build a TA binary. The binary is measured by TA builder and get a SHA-256 hash value. Opti builder offered signing private key, signing public key, signing key ID, sign ID, and develop attestation PTA on Opti. So this information are set to verifier by a provisioner for verifier, VERAISON. This slide shows the real VERAISON provisioning. So we have to set the signing public key, ECDSA key, TA ID, and hash value of TA binary, signer ID. This slide shows the remote attestation phase. At remote attestation phase, at first, CA send a request, send a request of remote attestation to line party. Line party forwards the request to verifier. Verifier send back to the request to CA with nonce. Nonce is used to trace the protocol. CA issued the API of remote attestation request to TA. TA use remote attestation API of PTA with nonce and TID, etc. Remote attestation PTA create evidence and send to the evidence. The evidence is signed by CBOR. So the verifier using the information and signing public key and decides the evidence is good or not. So the result is sent to Lang party. Lang party can know the device is good or not. So after that, Lang party establish a trust and make a secure communication. So this slide shows the current status. So the source code we developed are included in Opti original at November 22nd, 2024. The sample code is also opened. The sample code is used on QEMU and Raspberry Pi 3B+. So we are now trying to add these samples to Opti examples. So current version works on normal Arm Cortex-A TrustZone devices. However, current version has issues. The big issue is key management. Current version, signing key is created by Opti developer and included in Opti binary. So it is very dangerous because it can be extracted from the Opti binary. Because Opti binary is stored in normal storage, eMMC or SD card. So it is not good for supply chain security. In order to solve this problem, we developed a security enhanced version. So security enhancement version use HSM, hardware security module. Hardware security module guarantee the key is not outside the HSM. Current version utilize NXP Cortex-A CPU because it has CAAM, cryptographic accelerator, and assurance module. So this module is guarantee the key management. So this figure compares current general version and security enhancement version. Current version is general and can run QM and Raspberry Pi. So current enhancement version also has a pros and cons. As pros, CAM can create a signing key internally and does not expose the key. And CAM can create a signature for each ETA request. It is good for supply chain security. As cons, each evidence must create signing key during the provisioning phase. So the key must be registered at verifier for each devices. It is not scalable, so because there are many keys are managed by verifier. We are planning to next version to solve this problem. This problem will be mitigated by PKI-based key management. So I want to conclude my talk. So I explain the importance of remote attestation and TE on IoT devices. I report our implementation of the remote attestation OS with VERAISON Verifier. We have two versions. Current version is general and can be used on any Arm Cortex-A TrustZone hardware. Security enhancement version use hardware security module of NXP Cortex-A IMX8 and can run at Max Techno Armadillo board only now. So this version will be released soon. Please visit this homepage. Thank you. Thank you for your attention.
Thank you, Professor Suzaki. Do you have any questions? Okay.
In the RATS protocol, what are the mitigations for like spoofing the initial request to the verifier?
Spoofing, okay. Yeah, this is RATS protocol. I think spoofing is prevented by attestation private key because the Shiba format requires a signature. The signature is issued on attester devices only. It's a good answer.
I guess, but it seems like maybe there's still an opportunity that even in the secure enclave of the CPU, if you've somehow loaded malicious code, you can still just provide the hash of a binary that's not actually in memory.
Yeah, it's a good question because you assume the device has all same signing key, but our implementation create each signing key for each devices. Okay?
Okay, thank you.
Okay. So again, thank you, Professor Suzaki. We go to the next session. So again, please give him a big applause.
Thank you.